Did you get our little note that we had on the board?
No.
Somebody erased it.
Must have got erased.
Must have got erased. K-E-R-S, I told them not to erase it.
The last little part, I'm going to really run through 5 sections in 3 days. So Monday, Wednesday, and Friday, we're going to be covering 4.1, 4.2, 4.3, 4.4, and 4.5. But I'm going to be cutting out some of the stuff that I'm not going to worry about. I'm going to cut out all the graphing. You should be happy about that. I'm going to cut out all the graphing. And I'm just going to touch on some of the features of these exponentials and logarithms. And at the end, we'll solve some equations and then some kind of application on Friday.
I'm not going to be here Friday.
How horrible.
Are you going to?
I'll be taping it.
All right.
I'll be taping it, and it should be up Friday. If I can.
Your last one were not up there. No, not for 3. Chapter 3. It was on like 2.
Alright, so let's start off with 4.1. And we're probably going to get through 4.1, 4.2, and maybe a little bit of 4.3 today. I want to try to get as much done as possible in 2 classes, so that 3rd class we can have a little review session. Oh, by the way, Merry Christmas. This is the chapter for the final review. It only has 99 questions on it. You don't have to answer all 99. It's up to you which ones you want to practice. But I'm going to pull 25 to 30 of these for the final. Random, just choose ones I think are really, really important. So be careful. So here we are, 4.1. Let's see here. Exponentials. 99. That's not 100. 99. Like 99 bears about on the wall.
You can at least put 8.
Well, I'm giving you all the possible questions. You get to choose which ones you want to practice. Highly suggest the ones that you don't know how to do. Exponential functions. We have to go back and talk about the rules of exponents. You should remember these. A to the m times a to the n is equal to a to the m plus n. Base times a base, you take your exponents and you add them. Rule number 2 that comes in handy is a to the m over a to the n. M minus n. And if you have a to the negative n, 1 over a to the n. This one's important. It's actually a sub-rule of number 2 there. A to the 0, of course. 1. It took you all a while. 3. A to the m raised to the n. A to the n times n. Power to a power you multiply. That's the one you memorize so you don't screw up the plus one. And finally, it's not really one of the rules of exponents, but it comes in handy. A raised to the x over y is equal to, in radical form, a root. I'll give you that. What kind of root?
A Y root.
The y root. The y root of x to the, I'm sorry, not x to the, a to the x. Y root of a to the x. It doesn't come in that handy for our purposes yet. Okay, so let's talk about an exponential function. What makes an exponential function an exponential function? Now we're going to get a little weird. I need that last one for the weirdness that we're going to do up here. So an exponential function has this look to it. Something like that. Where a is just a coefficient, b is called, take a guess, the base, and x is called the exponent. Now, when we set up these functions with a variable x, we assume that x can be any real number. So x is going to range from negative real numbers, 0, positive real numbers. So we know everything about x. What about a? Can a be any real number to make this an exponential function?
Yes.
There's one number it can't be. 0. Because if it was 0, we wouldn't have an exponential function at all. So one of the conditions right off the bat is a, definitely, we don't want that to equal 0, otherwise we really don't even have an exponential function. What's wrong with this marker? I don't know. Yeah, stop. Now there's more conditions on b. What kind of numbers can b be? Can it be any real number? Well, it definitely can't be 0 again.
They have to be positive.
B definitely cannot equal 0. Why does it have to be positive?
Because they explain, I don't know.
Well, you're right though, but I'm going to explain why. Right off the bat, b cannot equal 0. There's another number I could care less about. Forgot your glasses again, didn't you? We really don't want b equal to 1, because 1 raised to any power is just itself. So having b equal to 1 is pretty pointless. That becomes, trivial. And why do we not want b to be negative? I'm going to put down here, b has to be strictly greater than 0. But why does it have to be positive? Why does it have to be positive and not equal to 1? Well, here's the reason. If I write this function, f of x is equal to negative 2 raised to the x power, where my base is a negative number, and we try to do a little table with it. Here's x, here's f of x. If we plug in negative 3, what is negative 2 raised to the negative 3?
It's going to give you negative.
Then you come back over here to this little starred rule. Negative 2 raised to the negative 3 is the same thing as 1 over 2 to the negative 3. I'm sorry, negative 2 to the positive 3. What's 1 over negative 2 raised to the third?
It's going to be negative in the denominator.
Negative. Make it easier. 1 over 2 cubed.
Negative 8.
Negative 1/8.
Okay, you want throwing all the 1 all out.
Oh, my lord. 1 over negative 3. I'm sorry, negative 3. Dang it. Negative 2 raised to the third power is the same thing as 1 over 8, but it's going to be negative. Okay. How about negative 2? You're telling or asking? Is it negative 1/4?
What raised to
Yeah.
what?
Raised to the second power.
It's going to be positive.
It's going to be positive.
Yeah.
Because it's raised to the second power. So this will be positive 1/4. Alright, negative 1. So that would be negative 2 raised to the negative 1.
It's going to be negative.
Stop that.
Negative.
It's going to be negative. Alright, negative 3 raised, I'm sorry, negative 2 raised to the negative 3 was 1/8. Negative 2 raised to the negative 2 was 1/4. Negative 2 raised to the negative 1 is going to be? Negative 1/2 calculator girl.
I thought that, but I
Alright, 0. If I plug in 0, what do I get? Negative 2 raised to the 0.
1.
Anything raised to the 0 is equal to 1. 1. What's negative 2 raised to the first power? Oh, stop it. What is negative 2 raised to the first power? Negative 2. What's negative 2 raised to the second power?
4.
Positive 4. What's negative 2 raised to the third power? Negative. Negative 2 raised to the third power.
8.
Negative 8. Negative 8. Alright. What's going on here? Well, for odd numbers, my answer is negative. For even numbers, my answer is positive. So this graph is going up, down, up, down, up, down. For every even and odd. Okay. What if I plug in fractions? This gets a little bit uglier. Let's say I take negative 1/2. Or even positive 1/2 for that matter. Now think about this for a second. This is negative 2 raised to the negative 1/2. That's the same thing as 1 over the square root of negative 2. What's wrong with that?
Radical.
You're going to get an I. Are we going to be able to plot this? It's not a real number, so not real. So we're going to have a hole in our graph. That's not good. But if I plug in 1/3, we get an answer out of that. It would be 1 over the cube root of negative 2 or negative 1 over the cube root of 2. We get an answer. So if our index in the bottom is even, we don't even get a real number. If the index in the bottom is odd, we're going to get a real answer, but it's going to be, well, negative all the time because it's going to be odd. So the problem here is not only is it alternating sign, positive, negative, but when we get into fractions with even denominators in the exponent, then you're always going to get this not real piece, and you're going to have these holes in the graph. So would you consider this graph nice?
No.
Heck no. It's up, down, and a bunch of holes, so it's not even continuous. So that's why we let b be greater than 0, so we don't have to deal with that weird graph that just is a bunch of individual points all over the place. They're not even connected. That's the weirder thing. All right. So with these conditions, we have what's called an exponential function. A cannot be 0, B cannot be 1, and it has to be greater than 0. B equal 1 is just trivial. All right, so for instance, if I have a function that looks like this, can I evaluate it? Should be pretty easy. What about f of 2? What would f of 2 equal? What do you do? Plug in 2. So you get negative 2 times 3 raised to the 2. Do you do negative 2 times 3 first?
Exponents first.
Exponents first. So try not to look at this and go, oh, that's negative 6 raised to the second power. That'll mess you up. So 3 squared, 9 times 2, it'll be negative 18. All right, what about f of 1/2? Now, what do you get to use? Calculator, or calculator girl back there in the corner. So this becomes negative 2 times 3 raised to the 1/2 power, also known as the square root of 3. So it would be negative 2 square root of 3 if you want to write it that way. Approximately?
You want a
Decimal? Yeah. Negative 3.5-ish? What about f of negative 3? Without a calculator. So this would be negative 2 times 3 raised to the negative 3. What's 3 raised to the negative 3 equal to? Put it back over here to this little law. Anything raised to the negative power, you just shove it in the bottom. So that becomes negative 2 times 1 over 3 cubed, which is better known as? Well, yeah. So it would be negative 2 over 27. Not hard, right? Now, what if I want f of pi? Can you do this by hand?
No.
Calculator comes in very handy here. This would be negative 2 times 3 raised to the pi power. Now, unlike a rational exponent, which we can define with radicals, this is an irrational exponent. We can't define it with radicals. So we're making a huge assumption that we can take two rational expressions and squeeze in pi. One of them would be 22/7. I think that's a little high. And the other one would be like 3.14. That one would be a little low. And the answer to those two would be someplace in between it. So there is a way of defining it. It's just not very friendly. Well, what's it approximately?
-63.
Really?
1.
0.1. I guess that makes sense because pi is really close to 3, and 3 cubed is 27, and 27 times 2 is 54. But it's a little bit bigger than 3. All right, so that's how you would evaluate an exponential function. So how about something special, a special base? Let's talk about it this way. There's this formula. It looks like this. Anybody seen this before? What's it called? No one remembers. You probably saw it like in 8th grade, I would imagine.
Rate time.
Compound interest. This is the compound interest formula. If you put money into a bank and it earns a certain percentage per month, like if you have a savings account and you leave $100 in there and it earns 1% interest, at the end of the month you'll have $101. Or no, well, 12% interest, you'd have $101. Because you'd earn 12% monthly would be 1% per month. And then the next month you would earn interest on top of your interest, and that's why it gets this fancy word called compound. All right, so let's say we save $1,500 at 6.5% compounded monthly for 10 years. Now the compounded monthly piece, that's what tells you what n is equal to. So this piece right here tells you that n is going to equal 12. What if it said compounded daily?
365.
It would be 365. Compounded quarterly. Quarterly. In other words, how many times per year? 4. Semi-annually. 2. Annually. 1, and so forth and so on. So what the word compounded monthly just tells you what the n is equal to. 10 years will tell you what? Time. And time up here is represented by? T. The 6.5% will become? R, the rate. 1,500 becomes? The P. And A represents the total amount of the count after 10 years. After 10 years in this case. So if we plug it all in, we're going to get A equals 1,500, parentheses 1 plus 0.065. Remember, percentages don't work in formulas. You've got to change it into its equivalent decimal. Divided by n, which is 12, raised to the 12 times t, which is 10. Now for your calculator people out there, you really do need to multiply the 10 times 12 first. Because when you do the exponent, if you leave them separate, it'll actually give you the wrong answer. So make sure you multiply these two together first. It's 120. 120. Okay. Type it in your calculator, get an answer. I'm actually wanting you to type something in your calculator. There you go.
Get a big number?
You should get something bigger than 1,500.
I got 16004.6.
I got something else.
I got 2868. 2868. 1,500 parentheses 1 plus 0.065 divided by 12 n parentheses caret 120.
You said you got what?
Mine said
2868.
You're not typing it.
What?
Yeah, that's what you got.
2868.
Okay.
Instead of all these.
Raised
I think I gotta put the divide sign.
Would you put fractions? Oh, you put the fraction one. Yeah, you can't do that. The fraction one assumes you have a whole number on the top and a whole number on the bottom. You can't use decimals in it.
Are we writing it out?
What's that? Well, it's money. If we're talking about money, this becomes, what was it again?
2868.
2868 point.
275.
It's money.
2,000.
How would you read this? This is $2,868 and
Yeah.
28 cents?
Yeah, if you round it out.
You have to. It's pennies. You can't go any. There's no such thing as a tenth of a penny. So this is $2,868 and 28 cents. Okay, what happens if I take n and I let it equal 365? What happens if I do that? Should it give me, 365, should it give me a larger answer?
We should.
I would suggest you multiply the 365 times 10 down there at the end before you start. So 365 times 10, 3,000. Oh, duh.
What did you change?
Oh, okay.
All I changed was the 12 into 365. This 12 and that 12. So just change this one and this one. The 365. Type it in and get your answer.
Okay. Why would you do?
I want to see what happens if I increase the compounding. Well, you get a little bit bigger number, nothing huge. Comes out to be 2873.14. Ish, 14-ish. So it went up, what, $5? Is that? So you went from getting interest 12 times a year to getting interest 365 times a year, but we only made $5 extra in money.
We changed that.
All right. What happens if we let n equal 5,000? N equals 5,000. 5,000. Parentheses raised to 50,000. So it'll be for 10 years. Do you think the amount of money is going to go up dramatically?
Yeah.
Probably not. You would think it would. I mean, n's being 5,000. You're getting interest 5,000 times a year, and you're earning interest on interest 5,000 times a year. Well, actually 4,999 times a year. So what you get? 2,873.30. Woohoo! We made 16 cents. 16 cents more. So it went up $5, and then it's going up 16 cents. Guess what would happen if I raise this up to 10,000? I bet it doesn't change at all. Well, maybe it'll change a little bit. Parentheses, caret, 10,000 times 10. 31 cents. It goes up to 31 cents. So it goes up a single penny. So what's happening here is the limit of n going off to, remember these limit notations from the rational functions? The limit as n gets larger and larger of this a function is going to equal a specific number. And it'll probably be $2,873.31. I can tell you in a second what it actually is. It's 1,500, 0.0, what was it, 65? Yeah, 31 cents. That would be the maximum number it would be. So this idea here says that as we increase the n on this function, it's approaching a very, very specific number, that 2,873.31. So if we break it down, the piece that is keeping it exactly the same has nothing to do with the p, but it does have something to do with the n's, because that's what's increasing. We're holding all the other stuff kind of constant, and the only thing we're changing is the two n values. So if we break this down, we're saying that if we take the limit, I'm going to just create a new variable x, of this, which is the essential piece of the compound interest formula, the 1 over n raised to the n part, then this must equal a specific number. Because it's doing the exact same thing as the compound interest thing is doing. Now, what's interesting about that specific number, it's like 2.71828, blah, 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 blah. Well, we define it to be, ooh, I forgot my infinity. To equal this number, e. Remember pi? You know, the symbol for pi represents 3.17, blah, 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 forever. It's an irrational number. The same thing is true about this e number. And you can type in your calculator this expression, 1 plus 1 over x raised to the x power, and then just take x to be 10, 100, 1,000, a million, a trillion. And what you get really close to is this 2.8 number. Now on your calculators, to get it, you have to go second ln. I might as well get used to the ln button. Second ln, type in 1 and hit equals. It should be 2.71828, blah, 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 blah. So that's the number e. That's the number e.
You said second ln what?
Second ln and then type in 1 and enter. Basically, it's e to the first power.
And it's what?
2.71828, blah, 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 blah. And it goes off forever. This is called the natural number. That e thing is called the natural number. Very, very important base in math. The nice thing about the function, base function with e, if you ever get to calculus, you get funny things like this. You get the derivative, it's called a derivative, you care less about it. And you have this thing called e to the x, and you're doing something to this e to the x. And the nice thing about this function is the answer is itself. And that's the beauty of it. You're doing something to it, but it actually doesn't do anything. So it's like an identity, if you want to think of it that way. And then there's this other operation, it's called an integral. It's an ugly little thing. And if you take the integral of e to the x, don't worry about the dx part of it, it's also equal to e to the x. So the e function is wonderful. Base e function is a wonderful function in calculus because it becomes the easiest one out of all of them.
So basically, you're going around the corner to get next door.
Yes. But, you know, there's this one, and you actually have to do some work for it. It changes it.
I'm glad I ain't got to take care.
Yeah, it changes it. So the only one that doesn't change is e to the x, which is kind of cool if you think about it. All right, so it's a very, very important function. And it's called the natural number for a reason. It relates into population growth, bacteria, things like that are constantly changing. Constantly changing. All right, so that's all I want to teach about exponential functions. So if you want, you can ignore anything about graphing exponential functions on that review sheet or in the text. Oh, we already did the natural number. Okay, next part.
Hold up, let me get that review sheet.
For those that were late, here's your 99 questions.
I got 99 problems, but this always used to be one.
4-2.
Working on my third sheet of paper for today.
These are actually more important than exponential functions. Logarithmic equations. Why do we need logarithmic equations? Well, what if I took my compound interest formula and I set it up this way? The problem with this equation, well, number one, it's actually very nice because it's a bunch of numbers and one single variable, and I've always taught you if you have a single variable, you should be able to solve for it. The problem is it's in the exponential position, and you've never ever learned how to solve anything in the up position. You've always solved for it when it was a polynomial or something down below that you could deal with. What's that? 12t, yes. Someone else keeps glasses. Okay, so we need to solve for this t thing, and I need a way of doing it. So if we simplify the problem a little bit, it's kind of like solving this. This one you should be able to solve.
3.
X is equal to
3.
3. What algebraic method did you use to solve that equation?
I just knew it.
No, you just knew it, right? Oh dear, that's just horrible because that doesn't make any sense. But actually you did use something. You said to yourself that if you have 2 to the x on this side, and 8 can be written as 2 to the third. We actually used a property of math to solve it. And that property is 1-to-1. You remember the 1-to-1 property? If f of A is equal to f of B, then what must be true? Well, A has to equal B. So here, x has to equal 3 by the 1-to-1 property. So you actually did use a mathematical property. It's just, it only works if you can get the bases exactly the same. So what happens if we can't get them the same? 2 to the x equals 40. Now you have to go in your head and go, oh, 2 raised to what power is equal to 40? 2 to the third is 8. 2 to the fourth is 16. 2 to the fifth is? Come on, just double it. 32. All you're doing is doubling. So 2 to the third is 8. 2 to the fourth is 16. 2 to the fifth is? 32. 2 to the sixth is? 64. So one of them is 32 and the other one is 64. So 2 to the, what was it, fifth?
Yeah.
And 2 to the sixth. What does this tell you?
It's in between
It's in between what?
32. From 2 to the 5th and 2 to the 6th.
5 and 6. The answer has to be somewhere between x equals 5 and x equals 6. What property is that, or what theorem?
Intermediate value.
Intermediate value theorem. So we can use the intermediate value theorem. It's actually the more proper form of the intermediate value theorem. If you have one answer high and one answer low, your answer has to be someplace in between. That's more closely relates to what it means. But does that tell me the exact answer?
No.
No. But it does give me a good ballpark figure that we could try 5.5, type it in the calculator, and bounce it back and forth until we get really, really close to what power gets you to the 40th, or gets you to 40. So we have to figure out another way of doing it so we get the exact answer.
Well, it's not going to be exact anyway.
Oh yeah. Well, more exact, as exact as you can get it with a computer. There's a way of doing it. It's kind of cool. So, if I let f of x equal this function 2 to the x power, I can create a function out of this base 2 to the x. And we know that f of x is 1-to-1. How do I know that? Well, every time I change that value of x, I'm getting a new y, a unique y. 2 to the first, 2 to the second, 2 to the third. None of them are going to be exactly the same. So it is a 1-to-1 function. What must be true then?
Something got to equal.
1-to-1 functions. What's the major property of 1-to-1 functions? They have
Same base.
and begins with an I. IV,
No.
IVER.
They have a inverse.
Ah, an inverse. Boy, pull out 2 letters. It must have an inverse because it is 1-to-1. Therefore, f inverse of x exists. That's another way of saying it. ... is there for triangle formation. So, if it exists, that means there is a function out there that will undo an exponential function. Okay? So, what happens if I take f of x, which is equal to 2 to the x, and I do something to both sides? I'm going to apply a function to both sides of this equation. On this side, I'm going to apply the inverse function. On this side, I'm going to do the exact same thing. I'm going to apply the inverse function. Remember compositions and all that fun stuff? Yeah. Here's a composition. What happens when f inverse runs into f? They go away, basically. It's an inverse property. What are you left with? The x inside. So the left-hand side becomes x all by itself is equal to f inverse of 2. Dang it. That's not what I wanted to do. Hold on. No. Blah, blah, blah. That's not what I wanted to do. I wanted to do my equation over here. 2 to the x is equal to 40. 2 to the x is equal to 40. Then I want to apply the function inverse to both sides. That's what I want to do. So if I apply the function inverse to both sides, it kind of gives me an answer of what the left-hand side should be. This is f of x. The green 2 to the x is f of x. F inverse runs into f of x, and you just get x out of the deal.
Why not you get 2?
F inverse of 2 raised to the x is equal to
Okay.
x. I mean, that's one reason I did this. So I didn't have to, but one reason I did it. So I have this piece here. It's the same as this piece here, so it must be equal to,
Either way, or
yeah, it's going to be equal to x. So you get x is equal to f inverse of 40. Now this, if you look at it right, I just solved for x. I got x by itself. The problem is, I don't know what f inverse is exactly yet. I'm going to come up with it. But once I find f inverse, I can evaluate x by just plugging in 40. It's a beautiful little function. So, what am I really trying to do? Rest of it, I got a couple minutes. What I'm really trying to do is create a function to do what I want it to do. So if you have this equation, 2 times x is equal to 14, how do you solve it? Divide by 2, which would be the multiplicative inverse. Or you can change it into English. This says 2 times a number is equal to 14. So if you want to undo 2 times a number, you take the number and you divide by 2. You do the opposite. You undo what was done. So if I have 2 to the x is equal to 40, this is 2 raised to some power is equal to 40. How would I undo it? What kind of language would I use? Don't think of it as a function. You want to think of it as just language. What you're trying to do here is say, if I was going to solve for x, I would say, what power do I raise, I should have used a different base, 2 to, I hate saying that, 2 to, to get, you got too many 2's in a row, to get 40. If I can create a function that answers this question, I've found the inverse, because this is undoing what was done. Okay, the way we're going to write this is log base 2 of 40, and we're going to say that equals x. So this question gets put into this form. The log is basically saying, when you see log or ln, it's saying, what power do I have to raise my base to get to a result? What power do I have to raise my base to get to a result? So for example, a simple one. If I have log base 2 of 16, what power do I have to raise 2 to get to 16?
4.
4. So log base 2 of 16 would equal 4. Because 2 to the 4th is equal to 16. If I write log base 10 of 100, what power do I raise 10 to get to 100? 2.
10.
10 squared
Yeah, you're right.
is 100. 10 squared is 100. If I have log base 5 of 125, 3. Because 5 cubed is equal to 125. Kind of easy, right? Except when things get weird. Log base 2 of 1/8. Yeah, similar. Log base 2 of 1/8.
So you basically saying what power do
It's
we
not
raise
1/3,
1/8?
because 2 to the 1/3 is the cube root of 2.
So we were saying, what power do we raise?
to
1/8?
2
Oh, 2.
to get to 1/8. In other words, you could rewrite this as 2 to the x is equal to 1/8. Fraction. There's a fraction, so what kind of exponent does it automatically have to be? Well, it's the only kind of negative. It has to be a negative. So this is going to be negative, and then you have to go, well, 2 what is 8? 2 raised to what power is 8? 3. So it would be negative 3.
So basically, every time we see a fraction, think
You're
negative.
thinking negative exponent with logarithms and exponentials. You're going to be having a fraction out of the deal. How about log base e of e to the 17th? You, staring you in the face. What power do you have to raise e to get to e to the 17th? 17. It's right there, 17. Log base e and e are inverse functions. When they run into each other, what happens to them? They go poof, and what are you left with? 17. Log base 5 of 5 to the negative 8th power. Negative 8. Makes life kind of easy when they're written that way. So if you look at this one here, you could also write this as log base 5 of 5 raised to the 3rd power, and that's the same thing as 3. Because the log 5 and the exponential 5 base would kind of go poof, and you're left with the exponent. So you might want to write this down. Rule. This is just one of them. If you have log base b of b to the x, the answer is going to be x. If you have log base b of b, the answer is 1. Because the power up here is 1. Log base b of 1 is going to equal 0. Because anything raised to the 0 power is equal to 1. B raised to the 0 power is equal to 1. Ooh, watch my finger pattern here. B raised to the 0 power is equal to 1. So, probably the main rule, very important, log base b of x is equal to y is the same thing as b raised to the... Well, what power do you have to raise b to get to x? Well, you raise b to the y, and it must equal x. This allows you to transform logarithms into exponentials and exponentials into logarithms. The only thing important here is you get your base b down first. What's on the opposite side goes one side, and the other side goes the other. You get the idea. It's going to be b to the opposite side is equal to the same side. If we wanted to change this into a logarithm, it would be log base b of x is equal to y. You always go backwards over the equal sign because you're taking the x's and y's and flip-flopping. What's that? No, it isn't. Got 3 minutes. And you were all late anyways. So for instance, convert
You never done that on the main problem.
which one?
Log 2.
Oh, we're not there yet. We're getting closer. We're getting closer. Convert to an exponential. Log base 7 of 2x minus 3 is equal to 5. The important thing is to label, in your mind at least, what the base is. That's the most important part. What is the base of this equation? It's 7. So you get that down first and you say 7 raised to what power? The 5th power, because it's on the opposite side, and it has to equal 2x minus 3. Guess what you can do from this point? You can actually solve for x. Because, 7 to the 5th is just some number. It's going to be big and ugly, but it's just some number. Add the 3, divide by 2, and you get an answer. All right, what if I want to go the other way? What if I have 4x minus 2 is equal to 8 raised to the 5y minus 1? How would I change that into a logarithm? Well, to change it into a logarithm, the first thing you write down is log. And then you determine what the base is. What's the base here? It's 8. That's the only thing that's in the base is 8. Everything else is a power or just a number. So the base is 8 of what? 4x minus 2. And it's equal to 5y minus 1. Ta-da. If you can do these two things, you can solve half of the equations I can throw at you without any blinking of an eye or sweating or anything like that. Because if you can change a log into an exponent or an exponential into a log, you can actually solve most of the log exponential equations.